Let's face it, sound is a weird soup, and we need to talk about Dan's dinosaur eggs. If you wanted to know the backstory, check out the links in the notes below. To summarize, in his video about how phase causes EQ and his following video about the chicken and the egg problem, he demonstrated that an all-pass filter that changes phase can be used to EQ a signal. And that is totally true, and here's why. Let's assume we have a very simple signal. It consists of only two fundamental frequencies, 220 Hz and 440 Hz. Our waves are described by sine functions. The amplitude A is the sine of 2 times pi times the frequency times the time, and also we add our starting phase, phi. The frequency and time term are only relevant for our wave to be able to wiggle, but we call everything inside the sine function the momentary phase of our wave. In this case, the starting phase is 0 for both fundamental waves. I will always write the 0 just to keep you reminded that it can technically change. Waves are superpositional. This means the order in which you add their parts together doesn't matter. The result will always be the same signal. If we look at a Fourier transformation of our green signal, we see sharp peaks for both those frequencies. Nothing else, because, well, there is nothing else. Now we want to make a copy of this signal. But in the copy, the phase of our 440 Hz wave is shifted by 180 degrees. Side note, 180 degrees is the same as pi. Our 220 Hz wave stays the same. The resulting signal looks different, but our Fourier transformation also looks identical. But does it? Fourier transformations have a real and an imaginary part. This is very important because only with the imaginary part the phase information can be stored. If we plot not only the absolute value of our frequency, but the imaginary and real part all by themselves, then yeah, both our signals are also different in the frequency domain. Green means real and red means imaginary in this case. In a spectrogram it isn't necessary to show you the phase information, therefore your everyday EQ will show you only the absolute value for each frequency. Now we can add our left and right signal together and we see the 440 Hz wave disappears. Like I said, waves are superpositional. It doesn't matter if we add the fundamental waves first or if we just add the full signals. If the 440 Hz waves are 180 degrees phase shifted and they have the same amplitude, this means their sum is 0, while the 220 Hz waves are doubled, and that's why I normalize the signal by dividing by 2. Let's take a look into the frequency domain, and the 440 Hz peak is gone, as expected. So, yeah, Dan was right about the first part. You can EQ with phase. Copy your signal, change the phase of the frequency you want to eliminate, add it with the original signal together, and the frequency will be less loud or even perfectly eliminated. But you have to be aware. If you change the phase of a frequency, you change the texture of a sound. You can hear that. Listen to our first example of just the 220 and the 440 Hz waves. First with matched frequencies, then with shifted frequencies. You hear that? They sound different, but the phase shift itself didn't cause the EQ. The superposition of both signals that have been differently phase shifted did. Now, with audio we are used to filter functions that shape our signals in the frequency domain. For example, a low pass function looks like this. We have the center frequency, omega 0. This is the cutoff frequency for a low pass. In our Q, this S is our frequency omega times the imaginary identity I. Usually, if you see an omega instead of F, the formula expects you to use the angular frequency, but in this case it doesn't matter since these two pi's cancel out anyway. Let's make a fast calculation. Our center frequency is 330 Hz, just between our both frequencies, a Q of 0.9 and no gain. Therefore, the absolute value of our resulting filter function looks like this. At 220 Hz we get about 108% of our original wave, at 440 Hz we get about 60%. Now we multiply our peaks in the frequency domain with those values, transform them back, and now the amplitudes of the 440 Hz wave is attenuated a bit. We can see our resulting waves look different, but there is still a bit of the 440 Hz wave shining through. But all in all, there was no need to introduce a phase shift. So, why do we keep talking about phase shifts made by an EQ though? Simply speaking, I cheated. When I applied the low pass, I acted like I knew the whole picture. I simply knew the signal from start to finish, got my spectral analysis and then applied the filter and, based on that, calculated how our new signal has to sound from start to finish. When we want to apply EQ in a live setting though, we can't wait for the song to end analyze the frequencies and then attenuate the ones we don't want. We need some smart circuitry that can reduce the desired frequency immediately, without having full information on the future of the wave. And that is how analog filters work. They take your incoming signal, duplicate it, and then start to introduce a different phase shift to all frequencies in each of the copies. I don't want to talk about the electronics here. I will put a link in the notes below though, so you can see a few circuits and how they do it. But in the end, your final signal will always be made of at least 2 delayed signals, where each frequency has been either shifted 180 degrees relative to its copy to cancel itself out, or by something else to get dampened a bit. And here comes the problem. By shifting the frequencies, we do not only introduce a relative phase difference between the copies, we also shift the overall phase relative to the original phase. And this shift is different for every frequency. Here I calculated how it looks for a second order low pass. While the duplicate of the 440 Hz wave is shifted relative to itself to attenuate itself, all the 440 Hz waves are also shifted against the absolute zero. And also our 220 Hz wave, which is not even smaller, has a phase shift relative to its initial absolute zero. We can calculate the phase shift an analog filter function is going to induce to each frequency by taking the arcos tangos of the real part divided by the imaginary part of the filter function. In this example we had a shift of -67 degrees for the 220 Hz wave and -106 degrees for the 440 Hz waves. And therefore our signal after the EQ looked like this. And this is usually what people mean if they say EQ causes phase shift. Now, does phase shift cause EQ or does EQ cause phase shift? Well, you can cause EQ by abusing phase shift, but the phase shift you get after an analog EQ filter in your final signal is not the same phase shift you abuse to eliminate the specific waves. And, by the way, those are huge disadvantages of analog EQ. You can't build one that doesn't have this flaw, at least as far as I know. But as you know, modern digital filters are able to actually reduce your frequencies without the need to shift the frequencies. Well, those were my 2 cents. If you feel like I got something wrong, let me know in the comments. For now, I want to thank Dan for his phenomenal work here on YouTube. There ain't many people who do more for our education on audio than him. So, maybe even if his egg laid a chicken, I'm thankful we have him with us. Happy Easter, by the way.